Welcome to this session on hybrid quantum classical machine learning models, a cutting edge area where quantum computing meets real world problem solving. We'll begin by exploring variational quantum circuits, the backbone of many quantum algorithms today. Next, we'll break down what is VQC and what are parameterized gates. Then comes the hybrid optimization loop. We'll also look at the circuit structure of VQC. From there, we'll move on to variational quantum eigensolvers. We'll talk about how VQE is used in quantum chemistry, and then we'll dive into QAOA. Finally, we'll explore some exciting variants of QAOA. Let's see about variational quantum circuits. They are quantum circuits with trainable parameters. They also combine quantum gates with classical optimizations. They are the core to modern quantum machine learning. Let's study about mathematical structure of VQC. We have an input which is classical data. We'll be taking input as classical data and then convert into quantum state with a parameter theta, get of phi of theta comma x. Here theta is parameter set, which will have a wide range of parameters. And then we have a cost function, C of theta. It is cost-specific objective. If we have energy objective, we'll have a different cost function. For loss objective, we'll have different cost function. Accordingly, we'll select a cost function. Now let's see what is VQC and common parameterized gates. A VQC is a quantum circuit that is structured as ket of phi of theta is equals to u of theta into initial basis state, where u of theta is unitarily composed of parameterized gates. What are common parameterized gates? These are rotation gates, either rotation around x or y or z. Here we'll be applying rotation on theta, which is a parameter which will change according to the cost. Why these gates? Why are we only using rotation gates? These provide continuous control over qubit state like a diode. They act like a diode. Small changes in theta will result in smooth changes in quantum state. Thereby, gradient-based learning is possible. The magic of PQCs lie in hybrid loop, which will help us build hybrid optimization loop. We'll see the set of steps which will help us build hybrid loop. Firstly, we'll have to set initial parameters, then run the circuit with these parameters, measure the results, thereby we'll calculate the cost. According to the cost, to minimize the cost, we'll update parameters classically. This loop continues till the cost function is minimized. Now let's study about the structure of VQC. We'll see the architecture flow. That is, firstly, we'll have data encoding. Here we'll have the classical data which is encoded into quantum state. This brings classical data into quantum state. Then we have a variational layer which will be applied on the quantum state. We'll have a parameterized circuit with parameter theta. We'll apply this on quantum state to make it modified quantum state, which gives the model flexibility to adapt. And then measurement. From the here, we'll measure the output, extract meaningful outputs, thereby calculate cost. To minimize the cost, we'll update the weights accordingly. Now let's move to variational quantum eigensolver VQE. Let me explain the quantum chemistry challenge. Here we need to find the ground state energy E naught of a molecule, and they gave Hamiltonian H hat that is equals to this part. We need to find ground state energy. In classical approach, we normally use diagonalized H. But here we face a problem. The matrix size will become too big. The matrix size will become 2 power of n into 2 power of n, which is exponential. So let's try on an example. For H2O molecule, we need at least 30 qubits. But when we apply that in classical, we'll get 2 to the power 30 into 2 to the power 30 matrix, which is 10 to the power 18 into 10 to the power 18 elements. which is really big. So we'll see VQE algorithm and how we can solve it using quantum approach. As a first step, we need to prepare the ansatz state, which is phi of theta ket equals to u of theta times phi naught of ket. And then we'll measure the energy, which is E theta equals expectation value of phi of theta, h hat, and phi of theta. And then classical optimization, that is theta star equals to argmin E of theta. Finally, we'll apply variational principle, which is E of theta star is greater than or equals to E of theta, which is exact ground state. This gives us quantum advantage because quantum computer prepares and measures quantum states. Classical computer optimizes parameters. Exponential, exponential space is explored efficiently. Let's now explore different ansatz used in quantum chemistry simulations. These are basically different ways of preparing the quantum state that approximates the ground state of the molecule. The hardware efficient ansatz is the general approach. It uses layers of rotation gates followed by entangling gates. It is not built with any specific chemistry in mind, it's more like general purpose circuit. The advantage is it's very easy to implement on current quantum hardware. But the drawback is it doesn't capture chemical structure or intuition. So while it's simple, it might not be the most efficient for chemistry problems. Coming to unitary coupled cluster, which is rooted in classical quantum chemistry. It starts from Hartree-Fock state, which is a good classical approximation of the molecular ground state. Then it applies exponential of excited operators, which essentially captures how electrons move from one orbital to another, including both single and double excitations. The advantage here is it's chemically accurate and theoretically motivated. But the drawback is the circuits are deep and have many parameters, making them hard to run on near-term quantum devices. So it's more accurate but also more resource heavy. And coming to ADAPT VQE, which stands for Adaptive Variational Quantum Eigensolver, instead of fixing the answer from the start, ADAPT VQE grows it iteratively. In each iteration, it checks which operator would most reduce the energy if added and adds only that one. So the circuit builds up only what it needs. This makes it like adaptive and efficient, especially for small molecules. The downside is that it computationally expensive classically since it calculates gradients at every step. Now let's talk about measuring the Hamiltonian, which is how we evaluate the energy of quantum state. Let's take molecular hydrogen as an example. Its Hamiltonian can be broken down into multiple Pauli strings, terms made of Pauli operators like Z, X, Y, and applied to different qubits. The problem here is each Pauli string needs to be measured in different bases, and we can only measure in one basis at a time. So, without optimization, this would require many separate quantum measurements. The solution is to group terms that commute, which means they can be measured together because they share the same basis. So, instead of measuring each term one by one, we group them smartly. Group 1, all terms that involve only Z operators, these can be measured in standard computational basis, no basis change needed. And then group 2 involving X and Y operators. For this, we apply a basis rotation using quantum gates before measuring. This way, instead of making four separate measurements, we only need two measurements, like two measurement groups, which is more efficient. Let's talk about QAOA, the quantum approximate optimization algorithm. This is a powerful quantum algorithm designed to tackle NP-hard optimization problems, the kind of problems where classical computers struggle to find solutions efficiently. To understand QAOA better, let's take a classical example, the max cut problem. We are given a graph, basically a set of nodes and edges with weights. The task is to divide the nodes into two groups such that the total weight of the edges between the two groups is as large as possible. But here's the catch. There are 2 to the power of n possible ways to split the nodes. That's exponential. So trying every possibility one by one, not feasible for large graphs. But quantum computers can help. They can explore all possible partitions at once. thanks to superposition. Let's now see how QAOA works. First step, we start with quantum state that represents an equal superposition of all possible solutions. Then we apply two kinds of operators. First, a problem Hamiltonian or cost Hamiltonian. This encodes the optimization problem we are trying to solve. Then, mixing Hamiltonian helps the algorithm explore different solutions by tunneling between them. That is quantum tunneling. We alternate these two operations multiple times and then measure the outputs. This sequence builds up a quantum state that concentrates probability on better and better solutions. See, if you see in this, in QAOA, we tune two sets of parameters. One set that controls the problem operator, the other controls the mixing operator. Each time we apply a pair of these operations, we call it a layer. So in each layer, we have two set of operators. One is problem, one is mixing. So it will have p layers, which will result in two p parameters. And interestingly, this number doesn't depend on the size of the problem. It stays manageable. Now let's see what does these operators do. The problem Hamiltonian or cost Hamiltonian gives us an energy penalty for bad cuts. Okay, and the mixing Hamiltonian lets us explore new cuts by flipping the nodes from one group to the other. This is quantum tunneling part. Together, they compete and guide the system toward better solutions. Let's now analyze how well QAOA performs. Even at the lowest depth, with just one layer, QAOA already performs better than random guessing. Let's see in this graph. This is circuit depth and this is approximation ratio. We are starting from p equals to 1. As we increase the number of layers, say to p equals to 5 or p equals to 10, the approximation ratio improves, meaning the solution gets closer to the optimal. You can see that at p equals to 10, the optimal solution, like the approximation ratio, collides with optimal solution. At high enough depth, QAOA can reach the best possible solution. So even the shallow circuits give useful results and deeper ones get even better. QAOA isn't just one fixed approach, it's evolving. Standard QAOA alternates between problem and mixing operators with shared parameters. Multi-angle QAOA assigns different angles to different edges, which allows for more flexibility and better performance. And warm start QAOA begins with good classical solution, then refines it using quantum updates. Coming to recursive QAOA, that breaks big problems into smaller ones like quantum divide and conquer. Adaptive QAOA uses machine learning to learn best parameters on the fly during the optimization. In this session, we have discussed about variational quantum circuits, their mathematical structures and parameterized gates, also about hybrid optimization loops and VQEs and their algorithms and how they are used in chemistry, also about QAOA, their architecture, performance, and different variants. To wrap it up, we say quantum classical models like VQE, VQC, and QAOA offer a promising path towards solving complex problems. And they can blend quantum power with classical control, paving the way for future of quantum computing.
Like and subscribe for more quantum computing videos.